Hi, good morning, everybody. So this is Hiromasa Takemura of the National Institute of Physiological Science in Okazaki, Japan. I'm also going to co-moderate this session with just Nicola. Then I think my talk is just including some tutorial for maybe those who are relatively new to this course or who wish to just better understand maybe how neuroanatomy will help us to understand neuroimaging analysis in general, but not only for that, I think also for understand maybe some building some model for information processing in the brain as well. So let's begin. I have nothing to disclose. So this lecture, we have some two learning objectives. First, so we want to ask you to better understand how anatomy will impact your neuroimaging data analysis. Then second, then we would like to just introduce how to understand, well, how anatomy will impact some existing model or maybe taking some visual processing as an example architecture of the information processing in the brain. So my talk has two parts, and first part is some general tutorial about how anatomy can be important for maybe neuroimaging data analysis and interpretation. Then second part is talking about some general impacts of the neuroanatomy on maybe computational model of the visual processing. So, well, we are just members of the OHBM, then I suppose that everybody gets very interested in the human brain. Then I think human brain during evolution has very just expanded organ compared to the brains of the animal model, say macaque and mouse. Then compared to the macaque brain, human brain has 15 times bigger volume. Then compared to the mice, it has just 3,000 times bigger volume. Then this expansion of the brain it just concurrently occurred with some evolutional expansion on particular anatomical feature in the cerebral cortex. So here a cartoon of anatomical image of the four animal species from mouse, marmoset, macaque, and human. Then you may notice several noticeable differences between them, except for the scale bar. But I think one of the biggest factors you can easily notice is a different complexity of the gyrification. Because as you can see, we know that rodent brain have a very flat sheet of the gray matter, no sulcus folding. The marmoset has kind of more smaller number of the sulcus folding. The macaque have considerably many number of the dips in the sulcus in the brain. Then I think the human brain has a very complex gyrification pattern existing in the surface part of the cerebral cortex. So that is notably just major part of the human brain neuroanatomy. So then anatomists label, I think these sulci and gyri, these structure with particular label. Then in order to understand how to navigate brain data in any dimension, it's better to remember some of the name of the sulci and gyri. Here I listed several noticeable examples in this particular coronal section. Then these are just very important to navigate yourself about where some functionally meaningful region you want to investigate exists in the individual brain. But also I think you can just easily just navigate yourself how I think brain just organized in a manner that just maintains some spatial arrangement consistent across different individuals, or sometimes it's not fully consistent across individuals. So, well, in general, there's some notion that if you understand location of the sulci, it can be a useful predictor to understand where is the location of the functionally meaningful gray matter area in that person's brain. Then one of the major examples in the literature is a tight association between calcareous sulcus and retinotopy of the primary visual cortex. So getting back to very older study by, I think, the neuropsychological literature, then I'm Japanese, so I just took a picture by Tatsuji Inoue. So he is kind of Japanese ophthalmologist, measures some brain lesion during war period. So interestingly, even it just get back to 1909, so he already discovered along calcareous sulcus, which is some medial part of occipital cortex, has some retinotopic representation. That means some loss of particular part of calcareous sulcus causes some visual field deficit in particular position in your retinal space. So this is the old paper. Then there are a couple other groups like Henshin and Holmes also reporting some existent retinotopy in our visual cortex. Then, which is nicely aligned with some modern visualization, say by fMRI, because now we can more easily see calcaneal sulcus in inflated surface space. Then along the calcaneal sulcus, we know that maybe more posterior part represents our central visual field, then more anterior part represents some peripheral visual field. Then this just gradient of the information was already reported back to early 20th century, but it's kind of a nice example how anatomy of the sulci is corresponding with some location of the functionally meaningful area. So there are a couple of other examples because if you are interested in motor cortex, you may heard about motor hand knob. So you can see this kind of arrow area, which is kind of little knob in some motor area. So this is a kind of predictor about where a hand representation corresponding area in the primary motor cortex may exist. So you can just use this gyrification pattern in the precentral gyrus as a predictor to the hand area. And there's a couple of other examples. This is a paper by Kevin Weiner, Gris Spector, Karl, Zilles, Katrin Amundsen, and others. Then they are investigating some sulcus folding within huge form gyrus. Because we know that in ventral occipitotemporal cortex, we have some huge form gyrus, which is a prominent structure in the human ventral occipitotemporal cortex. But within the huge form gyrus, so there's kind of relatively small sulci named the mid-huge form sulcus. So they just discover this mid-form huge form sulcus is a kind of major landmark for distinguishing different cytoarchitectonic defined region. But not only for that, this just border quite often aligned with some different functionally localized area, say fovea or peripheral, but it's also nicely corresponding with the face area in maybe more occipitotemporal sulcus side, and press area, which is more collateral sulcus side in the medial side. And this is a good landmark to distinguish where face area, press area may exist. However, there are a couple of caveats. So you can, of course, use some sulcus folding as an indicator about where some area boundary exists. But I think the prediction of the area boundary from cortical folding alone is imperfect even in the primary visual cortex. So this is a paper by Bruce Pissell and Karl Zilles and others. Then their vertical axis indicate they're just trying to use some cortical folding pattern for predicting some cytoarchitectonic boundary of the human just brain area. Then lower number mean, I think model prediction is better by folding. As you can see it in the leftmost is the B1. So B1 is so-called postal children. You can make a reasonable prediction by folding alone, but you can just still see some error at the level of maybe 2 millimeter on that scale. Then if you are going to B2, or if we are going to Brodmann area 44 and 45, I think prediction performance gets much worse. So you couldn't just reasonably predict the area boundary solely based on sulcus folding. So then you can just use sulcus as a landmark for functional area, but it's not always the case. Then even the best example is not that perfect. So how we can improve some prediction with the area boundary based on maybe structural data alone, because some research situation we can use functional localizer, like maybe face localizer, or maybe tapping just stacks for fMRI to localize some specific brain area, but it's just not always possible. Some area, I think that good localizer is not established. Then also getting localizer data is kind of expensive in terms of time of the scanner. Then I think if we are just using some free surfer Heinz atlas of B1, of course you can reasonably predict some location of the B1 as well. But this is actually not a perfect model of the primary visual cortex because it doesn't fully match with some manually delineated boundary in retinopic data. So we are now pushing just this direction forward with our collaborator Noah Benson, University of Washington. Then Noah Benson have provided a couple of atlases for fitting retinopic area prediction just for the structural data. Then if you are curious, you can just go to Noah Benson website. So he made a couple of existing software already available. But what we are doing now is just combining multiple input of either structural functional data, not just a sulcus folding, it's also using some tissue contrast. Then we are using some convolutional neural network to just predict some boundary between B1, B2, and B3. Then we found that this type of CNN-based some multivariate just prediction outperforms existing model just based on the sulcus folding, indicating there may be multiple factors contributing some area border. And I think the other part I think you need to pay attention is I think the sulci and gyri often affect interpretation of your neuroimaging data. Because major representation and neuroimaging, one volumetric, then other one is just called surface. Then maybe you can just visualize it in the inflated surface space. Then if you are checking some this green and red, you may just see some differences because in the volumetric space, then green and red are just 3 to 5 millimeter away, but in the surface space, it's just far distant. It's very different area. Then what I mean is, say, if we are performing spatial smoothing without considering a sulci and gyri, you can just easily mix signal between green and red. But looking at surface representation, this green and just red are very far each other. So therefore, in order to accurately just interpret your data or developing some accurate pipeline, I think it's very important to pay attention to the sulcus folding and how each just image processing affects just signal based on just this anatomical representation. And also, if you are doing some MEG, for example, then we know that MEG is more sensitive to signal from sulci because it's just picking signal current flow from some pyramidal neuron, making some orthogonal magnetic field. Then those dominant source of this type of signal is just coming from sulci. So therefore, general notion about MEG is more sensitive to sulci. Then if we are using diffusion MRI for tractography, then we also know that there's some considerable level of some bias based on the sulci and gyri. So therefore, just knowing about sulci and gyri and also its impact on your analysis pipeline is just important, not just for functional MRI, but for any of the modality in the field. So in the rest of time, I'm just going to talk about how neuroanatomy can help us to better understand information processing architecture by taking vision as an example. So anyway, so I have just two questions here. First, what is appropriate level of biological complexity to be included in the model of neural computation in the visual system? Then question number two is how we knowledge of neuroanatomy guide us to build biologically plausible model of neural computation. Well, what do I mean? So I think people always want to just build a model to better understand information processing architecture in the brain. Then simplest form is just making a very simplification because if we are opening some neuroscience textbooks, so you can see cartoon of the macaque brain, then you can see some simple dichotomy between some dorsal where pathway signal from B1 to MT or ventral what pathway traveling through the ventral occipital temporal cortex. So this is very simplest form. Or maybe other type of model may emphasize, you can just see this type of review paper, some feed-forward processing scheme from maybe retinal, LGN, B1, B2, B4, IT cortex. But of course, because I think these just cartoon model have some maybe simplification to just reduce information, this model typically ignore some existing anatomical pathways as well as existence of some major areas such as B3 and B3A. I think they're omitted from these just cartoons. So in other cases, people also try to make some anatomical connectivity diagram based on some non-anatomical information. This is a famous example coming from Ferrer and Bayesian diagram. So you see some hierarchical structure in there, but you can see some anatomical connection can be complicated. So, well, it's also important to just describe, I think, which area to area is connected, but my point is, we need to just build a model about this. So of course we can just see connectivity matrix, but we want to make some approximate some intermediate level representation, not too much simple, but not too much complex, which will be better for us to understand how these areas are connected. So how these areas are connected? So then I think here, the point is if you're looking at neuroanatomy, so we can see a group of axons traveling together, forming a bundle of axons. So this is called the 5-matter tractor fascicle. This is an example named arcuate fasciculus. So this is a very important unit of the neuroanatomy, which is kind of relating some particular 5-matter region with the functional roles. Well, there's kind of long literature about how 5-matter tracts are important unit to understand our brain functionality. For example, but back to the classical work, so we have some oral disconnection syndrome literature, like loss of particular fiber bundle causing particular functional loss. And also in the modern literature, this is a paper by Thibault du Chotin. So we can see some measurement of the diffusion MRI non-invasively to measure fiber tract. We can also see somehow this can explain variability in the behavioral data as well to understand function. So for this reason, I think maybe not just focusing on connectivity diagram, it's just better to bring some information about fiber bundle, like say five matter tract, into account to the model of the visual processing to maintain anatomical meaning unit. Then we want to just maintain some functional important region while we want to reduce some complexity as well. So getting back to old literature, back to late 19th century, there are some good series of the work reporting a fiber pathway named vertical occipital fasciculus. Hereafter I will call BOF. So this is one of the association five matter tract connecting dorsal and ventral occipital cortex. Then back to the late 19th century, it's just well described by a couple of just classical books, but it was largely ignored until recent human neuroimaging rediscovery. So therefore, anatomical detail and interspecies homology of this pathway remains largely unknown. So we just try to just measure BOF using diffusion MRI and tractography. So you can see some nice representation of pathway in the left picture, so which is a pathway overview from the coronal section in the occipital cortex. You can see that this pathway connecting dorsal and the lateral part of the ventral visual cortex. So the right figure is a sagittal section. You can see it's more lateral to optic radiation and posterior from arcuate fasciculus. So this is the architecture we can see from tractography, but which is nicely consistent with classical camera lucida drawing by Desjardins and others. Because here in the old textbook, we can also see it's a pathway connecting dorsal visual cortex and lateral part of the ventral occipital cortex. So we can just replicate old finding. But in the modern world, we can also try to estimate which area to area are approximately connected by this pathway in order to incorporate this fiber bundle into our information processing understanding. So this is kind of representation for inflating the cortical surface. Then we just delineate a boundary between different visual areas based on functional MRI-based just retinopic measurement to define area border. So as you can see, we consistently found the BOF has endpoints near the area called B3AB. Well, this is the area often omitted from the model. But we can see some prominence of the cortical endpoint of this pathway in this area and surrounding area. So then we are just rotating, then we are now checking some ventral side of the visual cortex, and again we just parcelate just brain area based on retinotopic measurement in depth MRI. So we consistently found the endpoint of the BOF is just located near fourth visual area HB4, ventral occipital cortex area 1, and a few other neighboring areas. So then luckily, I think later, this type of finding have been replicated by a couple of other groups. So this is a paper by Xu and colleagues. So they are using some different independent diffusion MRI data with some cytoarchitectonic based some parcellation scheme with more number of subjects. They basically reported some dorsal endpoint of the BOS are near B3A, B3B, and surrounding intraparietal and B3 area. In the ventral side, they also report some B4 and neighboring regions are kind of central part of the ventral BOF endpoint. Then here's kind of other paper published from Japanese group in Chiba University. So they're just using more traditional Klinger dissection protocol in the neuroanatomy, but they're just using some south side folding like POS or PTCOS. These are kind of sulcus landmark for predicting location for B3AB and HB4. So we can't just measure retinopathy from postmortem brain, but they just predict approximate location by looking at south side. They just start to dissect. Then if you are dissecting near maybe B3AB, you can nicely see some vertical occipital fasciculus in there. Then you can just trace down then all the way to PTCOS, which is some south side located near HB4B1 boundary. So there's some general agreement like this pathway is connecting some maybe mid-level visual area, B3A, B4, those level, and connecting some mutual information each other. So later, I think our service or a couple of other groups as well, I think trying to measure commonality of this pathway connecting dorsal and ventral visual cortex across different animals. Then we can see some nice representation of BOF in macaque diffusion MRI data, chimpanzee and marmoset as well. Then I have a chance to work with Nicola and Dr. Karl. They're working on some polarized light imaging neuroanatomy data from barbel monkey. We could also see it. And more recently also discover maybe this pathway may be present in the garago, which is kind of more ancestor kind of level of some primate just species, but it's still within primate just species. But it's kind of close to the border between just primate and non-primates, suggesting that this is just not only diffusion discovery, but this is a prominent pathway common across primates. So how this matter for function in the end? So there are a couple of just theory, but I couldn't just pick everything. But one was a kind of paper in K. Yetman and just attempt to incorporate existing of this just pathway into their computational model. So they're just measuring some task dependency on the ventral temporal cortex for word stimuli and face stimuli. They're just responding building some model for predicting maybe signal from intraparietal sulcus can just modulate some activation in the ventral temporal cortex. Then just try to estimate the location of the modulatory signal based on this mathematical model. They measure some IPS hotspots, and they just measure using tractography these kind of area included as a BOF endpoint. Then when combining this just anatomical knowledge, I think they could just say, maybe if we are considering this just top-down input from IPS to, say, BWFA, you can just better account some variance of the visual signal. Anyway, just try to wrap up. So I think that in contrast to simple diagrams that appear in the textbook, we nowadays just discover visual signals are exchanged between dorsal and the ventral visual area by vertical occipital fasciculus. Then this is just not some neuroimaging specific finding. It is actually a prominent feature commonly appear across a different primate visual system. It's not just simply maybe difference between human and macaque. Then macaque visual system also have prominence of this pathway as well. Then BOF may be involved with a barrier's visual function, but one potential example is it may potentially explain the signal source of the task-dependent activity modulation happening in the ventral occipital temporal cortex. So finally, I think the case study is one example about how to incorporate this type of pathway, which have been ignored in the literature, into the computational model will be an important next target of the visual neuroscience in order to go beyond the simple dichotomy between just dorsal stream and ventral stream. So anyway, so I would like to conclude with a take-home message. So first part, I hope maybe I could convince you neuroanatomy always matter for you for the interpretation of neuroimaging data regardless of your study goal. Then some of you are more interested in functional, some of you are more interested in anatomy, or some of you are just more interested in the molecular architecture, or some of you are interested in dynamic signal coming from MEG or EEG. But whatever your goal is, I think neuroanatomy is a kind of major component of the brain you always need to pay attention to achieve your study goal. Then I think that most of the schematic or computational model exists in the literature. I think it's not specific to vision. Most of them are very simplified by reducing biological complexity. For I understand for modeling perspective, I think that reducing complexity can be some benefit. But I think we know that in those situations, we actually entirely miss existence of some major anatomical structure or existence of the major communication between some noticeably bigger brain areas as well. So therefore, in order to understand some concrete model of the visual cortex, so we have to pay attention to how to balance to maintain simplicity of our theory as well as just anatomically accurate. Then I think that the understanding of the fiber bundle, like 5 matter tracks, kind of reasonable information for you to better understand what's a good anatomical substrate of your computational schematic models. Finally, I would like to thank some all lab members in my group, as well as all collaborators, including Dr. Karl. Thank you very much.
Wonderful, Hiromasa. Thank you for finishing on time. I forgot to say earlier on, if you want to, you can post your questions via the OHBM app. Otherwise, just put your hand up and we'll pass the microphone on. Hiromasa, there are two questions in the app already. The first one is, can the VOF be considered as the connecting white matter between visual where and what systems?
Yes, yes. So looking at some endpoint of the BOF, I think the area B3AB is an area considered for motion selective. So it's a part of traditional wear system. Then it's also terminated near area like BWFA. So visual world form area is a kind of categorical processing system. So in general, I think it's fine to consider as a pathway connecting so-called what and where system. But it's actually a little tricky. We have to pay attention because I think that dorsal and ventral, I think theory is sometimes a little too simplistic regarding anatomical position of the functionally meaningful area. Because traditionally in the macaque study, area MT, which is the motion sensitive center, is considered as a dorsal stream. Because in the macaque monkey, MT is all the way to up in the superior part of the superior temporal sulcus. But in human, we know that area MT is just coming to a more lateral side, somewhere in the middle to dorsal to ventral. But of course, it's considered a dorsal stream. But some people also propose some idea to categorize area into maybe dorsal, lateral, ventral. Then I think the literature is kind of slightly mixed compared with some older literature of the dorsal versus ventral. But in general, I think the pathway is connecting maybe area selective for spatial information and area selective for categorical information. Yes.
Thank you. We've got another question, which is, in terms of building anatomical models, what are the biggest obstacles to achieve them with today's algorithms, available algorithms?
Well, I think you can always make some semantic kind of schematic model, like some which pathway connecting where to where, then which pathway may correspond to some particular functional scheme by looking at brain region study or making some meta-analysis. But one of the complexity is if you want to make some mathematically quantitative model, then what is kind of strong barrier is you have to sometimes want to define arbitrary way to define so-called maybe connectivity strengths, then this is very arbitrary context because what is strong connection, what is weak connection? Actually, I have no idea because can you count axon or can you just measure FA value? Can you count streamline or can you quantify myelin? Then this kind of idea about which connection is strong or which connection weak is actually a little fragile concept. But for making sometime model, people want to quantify somehow to make a single number scalar value summary to describe area A to B connection. Then this is actually itself is challenging because truth of the neuroanatomy is just multidimensional. There are kind of different cell size, different axonal volume, or different just myelin thickness, then different just length. So it's actually not kind of single number summary, but some form of the computational model, just say people want to prefer to the single number summary. Then there's kind of big gap between actual neuroanatomy and single number summary. So maybe I think it's important to come up with maybe what's a reasonable strategy in between. Maybe we have to just summarize some information somehow, but maybe personally, I think it's better to avoid to all the way up to some single number summary because it's very difficult to make single number summary because anatomy is not just a simple phenomenon. So.
Thank you, Hiromasa. You made a very important point there, which is knowing how far to simplify matters to be able to create a model and explain things without losing crucial information. So simplification is good, but sometimes if you simplify too much, you're actually then passing on the wrong message, and that's bad. So, thank you.
Thank you.
With this, thank you very much.